Now students, the next type of atomic radius is the van der Waal radius. Now what is a van der Waal radius? It is, we can say, it is a half the internuclear distance between the two adjacent atoms of the two different molecules, or we can say of the two adjacent molecules in the nearby, right, of the same substance in the solid state. Now you can have the view on the definition here. What is the van der Waal radius? It is the half of the internuclear distance between the two adjacent atoms of same element belonging to two nearest neighboring molecules of the same substance in the solid state. Right, students? So here we will just first see that the two adjacent atoms of the element belonging to same nearest neighboring molecules. Now let us consider here that this is one molecule atom. This is the another atom covalently bonded. Right. Now the neighboring molecule. This is the neighboring molecule of the same substance, and here too the two atoms, they are covalently bonded. I think this is clear of the line that the two nearest neighboring molecules of the same substance in the solid state. Why the solid state? So that the molecules can come closer to a maximum, closer they can approach one another, right? So here we are going to find out the half. This is clear, this last line. Now the two adjacent atoms, this and this atom are not adjacent, this and this are adjacent, so we will take this one atom and this atom, right? And we have to take the half of the internuclear distance of it. This is the internuclear distance and this is just the half of it. Right, students? So half of the internuclear distance between the two adjacent atoms of same element. Now this element should be same. If it is A, this should be also A. This can be either same or different, right? Can be B or B, right? Or A again. Let it be in this way, right? In that case, this is the half of the internuclear distance, right, between the two adjacent atoms of the neighboring molecule. Now these neighboring molecule will be of same substance in the solid state. So student, this distance will be known as, that is from this one, will be known as the van der Waal radius. It is expressed in, written in this way, r van der Waal radius. Right, now the van der Waal radius, right, it is have the larger distance, then it is greater than the covalent radius. So we can say that covalent radius is shorter than the van der Waal radius, because in the covalent radius we have got overlapping of the atomic orbitals, which brings the two atoms closer, right? Whereas in the van der Waal radii, the two atoms are away from, two atoms between the two adjacent molecules of same substance, they are not close enough, right? They are not fused with one another, they are just away from one another. So that's why the covalent radii is shorter than the van der Waal radius. So just get it noted down. Now students, the next type of radius is the metallic radius. Now this is observed in the metals. In the metals, the atoms are arranged in a definite order in a crystal lattice. Now what is a crystal lattice? A three-dimensional arrangement of the metal atoms, right, having a definite pattern. So the distance between the two closest metal atoms will be considered here. So in the metallic radius, we take the half of the internuclear distance between the metal atoms, or two metal atoms in the crystal lattice. So what is the metallic radius? It is the half of internuclear distance between the two between the two nearest metal atoms in crystal lattice, right? So there will be an array of metal atoms like it is in this way, right? So I'm just showing it a pictorial representation where I am on the board expressing the two-dimensional representation of the crystal lattice, but actually the three-dimensional arrangement, right? So but on board it is possible to draw the here at this moment to draw the two-dimensional one. So here the two closest neighbor are these two, either this two or this two or this two, any of the two closest metal atoms. So we will take the internuclear distance, get it half, we will get the metallic radius. Now the metallic radius, simple you can write down our metal, the metallic radius, right? It will be greater than the covalent radius, right? So just a simple question to you all, that if you just compare the metallic radius, covalent radius and the van der Waal radius, which one is going to be of shorter distance, right? So metallic radius, covalent radius and the van der Waal radius, which one will be of greater magnitude? So here the covalent radius, hope so you are able to just arrange the series. So covalent radius will be shorter or shortest, then comes the metallic radius, right? And at last we have the van der Waal radius, so you can simply write down van der Waal, VAN, right? So these three mainly comprises the atomic radius, and we have one more expression of the atomic size, that is the ionic radii, but that we will discuss later. First we will discuss the variation of the atomic radius across the period and down the group, right? So far as atomic radius is concerned, we deal with only metallic covalent radius, metallic radius and the van der Waal radius. So we will discuss now the variation of the atomic radii across the period and down the group. So next we are continuing here, variation of atomic size or radius, right? So this we will first have the across the period. Now students, generally the atomic size on moving across the period from, we can say, group 1 to group 17, will not include group 18 here. Now from group 1 to group 17, when we move across the period, in a period, the atomic size decreases, right? So on moving across the period, atomic size decreases from group 1 to group 17, right? So can you tell why? Because here there is the increase with every increase in the atomic number, there is increase in the we can say increase in the nuclear charge. The one electron will be added. With increase in the atomic number, there will be increase in the number of electrons, right? in the shells also, right, in the same shell, and the simultaneously the number of proton in the nucleus is also going to increase, right? Therefore the effective or nuclear charge increases and the shells are being pulled in. Right, students? So, on moving across the period, there is decrease in the atomic size because due to increase in the nuclear charge, definitely there is increase in the number of the electrons also by 1 unit, right? But the magnitude of the nuclear charge which has been increased in the nucleus, right, it dominates, and the electrons on the outermost shell they are pulled in, so as a result the size decreases, right? But in case of group 18, because group 18 also belong into the same period, but in case of group 18 we will not consider the covalent radius. Here we are going to consider the van der Waals radius, right? So that's why there is an increase in the size of the group 18, right, with respect to that of the group 17. So from group 1 to group 17 we are considering here the covalent radius, and for group 18 we don't have a covalent radius, we consider there the van der Waals radius, which is larger in magnitude than that of the covalent radii. Now next is the down the group. When we move down the group, so what happens? There is increase in atomic size or radius on moving down the group. So students, here what happens that with the increase in when we jump from one period to the another period, right, that means when you're jumping down the group, then there is increase in the atomic number, right, and the new electron or the incoming electron is added in the new shell, right? Definitely the proton is also increasing, but the increase in the shell predominates here the nuclear charge attraction. As a result, what happens, there is an increase in the atomic size of that element, right? So we have discussed here the variation of atomic radius on moving across the period and on moving down the group. Students, you will just get it noted down in your notebook where you are discussing the atomic size, their types, right? How many types, what first will be the how you're going to define an atomic size, right? And why can't we just get the radius of an atom, right, simply, and we can just write that the atomic size can be expressed in terms of atomic radius, or it is the distance or radius of an atom is called as atomic size, right? Why we can't say so? So we have discussed it that since the atom cannot be isolated, it's too small to get it measured down, then the probability distribution curve tell us that there is no well defined probability boundary diagram doesn't tell us about, there's no well defined boundary of an atom, and the atom is not always surrounded in this with the same environment. There is always a change in its environment, and the bonded state is also going to change, right? Students, you will mention there is all state and then you will express it, that hence that's why we are having the atomic radius expressed in term of at covalent radius. Then we have got the van der Waals radius and the metallic radius, right, students? So that this thing you will get it noted down in your notebook.